So today I'll talk about shortly on the GaN power ICs that here in IMEC we are developing for power electronics. So we all know these days gallium nitride is gaining a lot of attention. That we also see that for its increasing market share and its availability in a huge applications, it is available. And why gallium nitride is gaining more attention, we all know by now, I guess, because of its high switching frequency capability, high breakdown voltage, and low on resistance, what makes it a more compact, more efficient design, especially in power electronics. But uh, instead of all these benefits, there are some problems to actually driving this GaN FET and to utilize the full potential of this technology. I will start with these challenges, what we need to face to use this FET in power electronics circuits. So to start with, that it has a low gate overdrive. It means that we are very much used to with the silicon MOSFET by now, where we have quite large gate overdrive voltage instead of in case of gallium nitride, that's not the case. So it turn on around 2.5 volt and then maximum 7 volt gate voltage. So it gives a narrow range of overdrive. So that's not only problem that driving in such a small range, it also impacts the high side supply for a half bridge. In fact, that calls for a new type of driver design. Besides that, because of its high switching frequency capability, it also have a high DVDT and DIDT transitions. That causes EMI issue, and also it impacts the switching performance. So gate ringing, it's a common phenomena to driving GaN. Besides that, the low gate threshold voltage, that is also because of this high DVDT transitions, we often see that it causes false turn on, especially in case of high switching frequency operation. That also impacts the switching loss and the behavior. That also impacts the behavior of the circuits. So it's clear that to utilize this GaN FET at its full potential, it's important to have an optimized gate driver design which can overcome these limitations. And also it is crucial for the system efficiency and the robustness of the entire system design at the end. Now, what kind of what we see, for example, if I want to show you a little bit in detail about these things I was just talking about. So for example, that I have a power HEMT that is driven by an external gate driver, then there is some parasitics in between this gate driver and the gate of the FET. And that creates an LRC charging path while the transistor is turning on. So while the transistor is running on, the current is actually flowing through the gate capacitance, and then is going to driver, and that LRC charging path is basically causing gate ringing. And this ringing is sometimes so pronounced that it is also affects the stability and the switching performance, even it goes to the load of the converter or the circuits you are using with. That's basically also a reason to increase the EMI issues. While it's turning off, we see that while it's turning off, it's discharging the gate capacitance, and because of the high DVDT transition. Also, as I said, that gallium nitride has an ability to work in a very high breakdown, and also because of the high switching frequency, it automatically gives a high DVDT transitions. And because of that, we see that sometimes that while it is discharging, it's charging CGS, and then it creates a peak during switching it off. And this peak is high enough to cross the threshold, and then we see the false turn on issue. So one of the easiest solution will be probably reduce or eliminate these parasitics in between the driver and the power hem by integrate both in a same IC. So that's one of the motivation to go for a monolithic integration, which helps to reduce this gate loop inductance, driving issue, the gate ring. It can eliminate or reduce the gate ringing to a good limit actually. So besides that, it's of course that if we go for the GaN IC, it enables the higher frequency operation because it can integrate higher power, and because it can, so the more power integration it is faster and enabling high switching frequency, and that because of that um, it also call for a compact and cost-effective design, because the higher the frequency is, the higher the power density is. So it means that the parasitic, it means that the passive components are also the size is reduced and also the cost is reduced. Because the parasitic reduces, and that reduces the gate ringing and the switching loss, so that leads to a more efficient design. So more efficient utilize of semiconductor switch, that means the more efficient circuit and the system design. And then because of the reducing gate overshoot undershoot, it's easy to control and lead for a robust circuit. So therefore we are convinced that if you want to utilize this gallium nitride technology in power electronics application, it's best to monolithically integrate this. And that's how we have started working on GaN-IC. And of course, we have faced several challenges to make all GaN-based IC design. In my talk today, I will show you like what are the different challenges we have faced to have realize all GaN-based GaN-IC. And then I will show you some basic GaN-IC demonstrators. And at the end, I will summarize my talk. So the challenges I divided into two parts is, one is like a technological challenges and another one is circuit level challenges. So in case of technological challenges, to start with that. So first, if I say that what do I mean by discrete components to GaN IC? Let's say if we want to have a half bridge switch and we want to drive that with a driver, so we have two discrete level power hem that are connected in series to have a half bridge switch, and then that is driven by an external driver, so everything is in discrete level. And this is a 3-die solution, and then we can go for a 2-die solution by first integration, either one power hem with this integrated driver, and then both of such ICs are connected to have a half bridge switches with driver, or we can have one IC where a half bridge switch is integrated and an external driver. We can go even further to have a 1-die solution where we can integrate everything together. So we are basically working towards that, where we can go from the 3-die to 1-die solution and everything is in all GaN based. To start with technological challenges, the first thing we see is a backgating effect. Now this is not something new. It is also we see in MOS. So when there is a voltage difference between the substrate and the source, then we see a backgating effect. And that is a similar thing we also see in this technology. In case of a E-mode HEMT, let's say for an example, if we have a half bridge switch and we have a common substrate, and then the common substrate is grounded. So let's say if the situation is something like that, that when so in case of half bridge switch that the switches are operating in a complementary fashion. So it's either of switch is on and another one is off. So let's say an example where the V in, so VDD here is at 400 volt and the high side switch is on and the low side switch is off. And that time the substrate is in 0 volt. And so the source of the low side switch is in 0 volt and there is no problem in case of low side part. But in case of high side part, when the high side switch is on, we see that the source of low side is 0 volt. So substrate is 0 volt, but the source of high side is very high voltage, and then that creates a current in the substrate, and then that we see a pronounced effect in case of I mean pronounced backgating effect in case of a high side switch. If we disconnect the substrate and if we keep it floating, still we will have a high voltage in between the source and substrate, and that can cause a backgating effect. So if we go for a higher voltage, we can see a backgating effect. However, it's not pronounced for 50 volt and lower. Besides that, we also needs to realize the different low voltage analog circuits that needs to be integrated in case of a GaN-IC realization, and also some suitable passive components we are working to have the monolithic integration possible. So in order to avoid this common substrate problem, what we have worked on, we worked on like a SOI substrate for isolation. So in this case, we have silicon 111 and the silicon substrate which is isolated by a trench isolation, a box oxide. And then you see here a low side and the high side switch are integrated in an SOI substrate where both of the source have its dedicated substrate which is connected with a 111 silicon substrate, and then that is isolated by this trench isolation. So basically in a two different pocket, both of the switches has its own substrate, and therefore it is possible to have the source and substrate at the same voltage, no matter if the substrate of the high side source and the substrate of the high side switch is floating. So that's how we eliminate the backgating effect, and that means in a simple circuit, if we have, let's say we have integrated a power HEMT with a driver, and then we use like two different pockets, and then yeah, that's how the substrate and source are connected. So that will be also repeated when we have a half bridge switches. So there are two pockets in between the low side and the high side switch, and so on. So for the low voltage component, so we have like the logic P-GaN HEMT that is up to 20 or 30 volt to have in the analog part, that we realize from our high voltage logic P-GaN HEMT that is derived from the shorter gate width and of course the shorter gate to drain distance. We have tested up to 2 micrometer gate width, and we see that the threshold voltage is unaffected. So these logic P-GaN low voltage devices are also part of our PDK. And then besides that, we have two different type of resistor. We have the high ohmic resistor. We have low ohmic resistors. So high ohmic resistors are realized by 2DEG, and the low ohmic resistors are by the different metal layers. And then we have MIM capacitors, which is like 0.33 femtofarad per micrometer square. That is all these like two different type of resistor and capacitor are part of the PDK that can be used to design the analog circuits. Besides the circuit level challenges, another main important thing is the circuit level challenges. We do not have a complementary device like we are used to in case of a CMOS technology. We do not have PFET, for example. It's only NFET. So that is the reason it is not possible to realize a TTL logic. Therefore, to have a GaN-IC, we need to work with a register transistor logic. That basically creates an issue because it's like a trade-off between the switching speed and power dissipation is needed by dimensioning the registers. That creates difficulties in driver design and any kind of logic gates or the sub-circuits on that node. So if I see that this is a building block of an analog circuit in case of a GaN IC, and in this case, what I mean that the limitations by using the RTL based circuit, in this case, we see that how this works actually. So when the transistor is on, that time we see the output is low, and when the transistor is off, then we see the output is high. And that's how it is working as a basic inverter. And this basic RTL inverter is a building block for the analog circuits. So here we see that the load resistance has a crucial role actually to realizing the gain and the delay and the power dissipation of the circuit. So if we increase the load resistance, so it increases the gain and the transition delays also increases. But then it also decreases the VOL and the power dissipation. So if we want to decrease the power dissipation, one option is that we can increase the resistance size, but then that comes with a penalty of transition delay. So basically, compromising these two parameters by using a resistance makes it more challenging to have a GaN IC circuit. We have some different type of demonstrators. We started from the logic gates. We have used, as I said, there's a typical RTL inverter block. And then we have seen a different type of inverter logics, what I've shown here, different type of, we have also realized some comparator op-amps by using these things, and we measured that. This is a picture of the fabricated one, and we see that yeah, we have a different publications. If you want to go through in the details, you can check the circuits and the logics and how it works. Here I will just show you one low side HEMT with integrated driver. So it is a basic output stage of a driver, and then we have tested in our lab up to 20 megahertz. You see in the around the 20 megahertz, yeah, it has some distortion. However, it works. And it's a double pulse test where we see that yeah, it up to 10 megahertz, it's working very, very good actually. However, it's unpackaged. It is like a chip on board bonding, and then we tested in even different converter circuits, and we see that it gives fast response, and also yeah, the ringing and everything is quite controlled. We also have some integrated driver with hybrid circuits. Here I have shown a result where you see that it is working up to 1 megahertz with a rise time of 25 nanosecond. The measurement result is a basic output stage of a driver with an integrated of level shifter. And here in this case, we have a non-isolated level shifter used. It is realized in the 200 volt half-bridge switches. We have GaN-IC technology, GaN-IC in different technologies like 200 volt, 650 volt, and 100 volt technology. We have some of these samples available through SN Plus project. You can visit the website to see that which samples are available. So we have some discrete devices available that is for the 200 volt, and yeah, we are now giving also 650 volt samples available, also half-bridge switches 200 volt, and bare die integrated driver with a low side HEMT, and that's only on 200 volt technology. Besides that, we are also, I mean, giving access to our low cost prototyping runs through MPW service, where you can get, so we have two runs in a year. One is like 200 volt GaN IC, another one is 650 volt GaN IC. through the SN Plus, you can apply for a TA, and if it's accepted, then you can get access of one of the small block in our MPW service in either of the technology, and there you can make your own design, and that can be fabricated in IMEC GaN-IC technology. So in today's talk, I have briefly mentioned of the several challenges to realize a circuit in all GaN-ICs and the different factors we needed to consider to realize this monolithic integration. We are also working on a second version of GaN-IC, where we are planning to include, so in the last year IDM, we have a publications where we are planning to include more components to make it more efficient GaN-IC. So for example, we are working on the Schottky barrier diode to be integrated, D-mode HEMT, the low voltage D-mode HEMT, so that for example, that if we have a low voltage D-mode HEMT, we can have a DCFL logic, direct coupled FET logic, which can give an improvement in some cases compared to the RTL logic. So the resistance can be replaced by a D-mode HEMT, then it will be a D-mode pair. I think in future that will be also integrated and will be available in MPW service. So that's it from my side. And thank you everyone for listening.
Just wondering, would Tobias be there?
Absolutely.
Oh, thank you, Tobias. Over to you.
All righty. All right. Thank you very much for the possibility to talk today about our silicon carbide technology and to also give you some insights into future power device development, especially the technology part that is required there. And then even would like to show you something about the integrated circuits that we are also implementing on silicon carbide today. And Fraunhofer IISB, as one of the Fraunhofer institutes in Germany, we are working on wide bandgap for power electronics along the whole value chain. So this basically includes material development, prototype design, and then even going through the assembly to modules that are basically then used in electric vehicles, for instance. And we do have a 150 millimeter silicon technology platform where we can do small volume fabrication from research and development up to prototypes. So in today's presentation, I will like to give you a short overview and introduction about exploiting the benefits of silicon carbide power devices. I'm pretty sure most of you have already heard about its application in traction inverters for electric vehicles, but today I want to go a little further and make an example with DC grids, which is another possible driving force for silicon carbide if the cost of the devices become lower. And this will basically then switch or lead to a discussion of what can and must be done in silicon carbide to basically follow this route towards more and more competitive devices. And on the other hand, I'd like to spend a few minutes on some applications beyond silicon carbide power devices. And this is basically the silicon carbide CMOS technology platform, high temperature, high voltage, and maybe even going to quantum devices. And then I will summarize my presentation. So besides the efficiency gain that you get for using silicon carbide in traction inverters for electric vehicles, where you also have a high benefit of smaller and more lightweight components. Technically, the energy efficiency is also true or exploitable for other energy conversion applications, especially where partial load conditions are a topic. So where basically you're not running 100% of the rated current all the time, but there is basically some sort of load dependent energy consumption. Electric vehicle is the best example because usually you're not accelerating all the time when you're driving the car, but most of the time you're idling at somewhere maybe 20–25% of the efficiency. And there, this silicon carbide material, being a unipolar device, has a significant energy efficiency benefit over using silicon IGBTs. And this is particularly true if you're transferring and storing energy between generation and consumption, because you're incurring these losses multiple times. So with the goals of carbon dioxide reduction, for instance, and energy efficiency, as we see more and more laws and regulations coming into place, the availability of these wide bandgap materials as an enabling technology will also see more and more regulatory benefits, besides prestige from Tesla, for instance, for being the first car company that uses silicon carbide. Of course, responsibility for companies becomes more of an issue in the economic aspects of the market as well. And in order to achieve the future CO2 reduction goals, I believe that wide bandgap materials, both silicon carbide and gallium nitride, can provide a significant impact. Also note that typically silicon carbide and gallium nitride are referred to as competitors, but if you look more closely, usually the big overlap is between silicon and the respective wide bandgap material. So silicon carbide naturally excels at voltages significantly above 600 volts due to the low device resistance that you can get. Silicon carbide has also demonstrated high reliability and the potential for cost reduction. And what we really want to exploit here in silicon carbide, which is also part of the beauty of this activity, is that we can basically use silicon know-how and ideas and device concepts and just transfer them to silicon carbide, which both includes trench power MOSFETs, IGBTs, and then CMOS technology, where a lot of work has been done in the past in silicon carbide. And I'll come back to that in a moment. Just want to point out that also the power market, or the IC market for power devices and silicon carbide, is ramping up now. A lot of companies have announced fab extensions. We even see some pure play foundries that are offering their fabrication services like the X-Fab or Classic. So at the moment, it's a very ambitious and euphoric activity to work in silicon carbide and bring products to the market. And of course, at this point, the demand is higher than the supply. So technically, you can sell pretty much everything and you will find somebody who buys it. And the question really is whether this will be true in 5 to 10 years as well, as we will probably see more and more production capability and then a saturation of the market at some point. And then, of course, the hockey stick sort of at some point will come to an end, and you have to consider yourself in competition with other companies and industry that might have more efficient devices, smaller devices, more cost-efficient devices, which then will also be the door opener to apply silicon carbide in applications where you don't get the grave benefit that you see now for electric vehicles, but then also for static energy conversion, for instance, PV, wind power, electrical storage, where you already see, for instance, silicon carbide Schottky diodes being used. The full silicon carbide solution using a silicon carbide MOSFET as well will become more and more lucrative on the long run. And just to give you a quick impression of some developments in silicon and silicon carbide, because there's an interesting parallel or anti-parallel in that case maybe. Most of the silicon technology circled around bipolar during its invention and development. Even TTL logic, things like this, silicon sensors that actually spun out of that. And then starting in the 1980s, the CMOS technology started to grow, which is still the backbone of today's information and communication technology. Out of that, high voltage devices, BCD processes or power discretes, and also the RF LDMOS high frequency transistors in the power in the information transmission, GSM, for instance, were introduced. And then also silicon discrete power devices like the VDMOS and the trench MOS, and then superjunction devices. And interesting enough, in silicon carbide, this actually goes vice versa. So a lot of effort was spent since the 2000s to develop silicon carbide power devices for its benefit. And that basically had to powered all the development, which led to high voltage power devices, bipolar devices, but also trench MOS devices here. And then on top of that, we also start seeing silicon CMOS circuitry becoming more and more appealing, because if you have an NMOS device, I mean, adding a PMOS is quite some work, but not an unsolvable challenge. So from that, we also see high voltage CMOS technologies, silicon carbide sensors based on the CMOS technology with integrating sensors and amplification. And then of course, also exploiting a key benefit of silicon carbide from its wide bandgap nature. Other than the high power, high voltage capabilities, is actually much less p-n junction leakage, which makes it also very appealing for high temperature circuits, which would not even run in silicon due to the high leakage currents. And to start with, we'll be looking a bit about the power devices now and what's going on here in the development. And there is basically technology development going on for a long time. I think most you might be aware that channel mobility, field effect mobility in VDMOS in power transistors, MOS transistors in general, is not very high when you compare it to silicon. So there has been significant effort trying to remedy this issue. And one of the solutions actually is just to put in more channels per area, which will also lead us to the trench MOS device in a moment. But of course, the design basically for this 1200 volt device is usually somewhere in a trade-off region where you have some drift region resistance, where you have some channel resistance and so forth. So reducing the channel resistance has a significant impact on device resistance reduction overall. So basically everything that you've done that you may know from silicon, you can also apply to silicon carbide power MOSFETs here. But then basically to move beyond a standard VDMOS transistor, where you can basically make a decent power device, if customer is willing to pay for this effort. Of course, there is the question of what else is presently underway and what steps are being taken to further reduce the cost of silicon carbide devices as volume goes up. And similar to silicon technology, first thing we do usually is to reduce on-device resistance to make it more, basically reduce the chip area that you need for a certain current density. And this is basically similar to silicon done by exploiting trench MOS technology, so that you can basically push the channel limit from the planar device to the trench MOS by just basically integrating more trenches per area. There is actually a wide range of trench MOS transistors being discussed at the moment, and feels like every company has its own idea of what the perfect trench MOS device will look like for scaling and performance capabilities. So there is not one device type as a general solution, but different companies really try different approaches. But what is common to all of these approaches is that basically the oxide in the trench structure here needs to be protected from the high electric field that silicon carbide is actually exerting on this dielectric, which is quite a difference to silicon, where the electric field is so low that the oxide wouldn't even notice basically avalanche breakdown occurring here. But silicon carbide is quite different from that. And this also includes processing optimization, hydrogen etching, different integration approaches that are being used here. Basically then also some examples of fabricated devices that, for instance, we are also working with industry partners for technology development in this field for this kind of highly integrated devices. In parallel to this, of course, another task at hand is to ensure that such devices are reliable, manufacturable, and in regarding applications also rugged. And this is basically achieved by ensuring typical reliability by, for instance, for the gate oxide is shown here, gate oxide screening and burn-in tests, the substrate defects or the epi defects play a major role that have to be investigated. So most of the know-how that we know from silicon, we can actually transfer to silicon carbide, like the TDDB tests, but there are then additional tests, especially to consider faster switching compared to silicon IGBT, for instance, that usually are added on top to ensure that these additional constraints and applications that silicon is usually not experiencing still works well in silicon carbide, because this has not that much been investigated in silicon. And considering that the first market silicon carbide is really addressing is automotive, which usually has among the highest requirements for reliability, I mean, not going to space applications or aerospace, things like this, it is quite a challenge to ensure that you can meet something like a 1 ppm failure rate for a certain mission profile if you don't fully anticipate the mission profile yet. So these kind of qualification efforts really also are a major contribution in the effort to providing reliable and well-performing devices. Manufacturability, of course, also goes to technology development to help ensure gate oxide reliability. There's a long story here with thermal oxidation of silicon, then basically considering nitrous oxide passivation, like the hydrogen anneal in silicon to passivate interface states, which the nitrogen is doing. Unfortunately, that also gets incorporated into the silicon dioxide. And then the idea is to maybe use a carbon dioxide post-nitridation anneal, and the story basically goes a little bit on and on. Mainly because the final or the ideal oxidation recipe in silicon carbide has not yet been discovered. While in silicon, everybody knows you make a 900-degree oxidation in a forming gas anneal, maybe something with chlorine in there, and you can readily buy some equipment that the equipment vendor will already provide you with a nice recipe for that. And I mean, we're basically talking about 1980s in silicon for silicon carbide when you compare it to silicon technology. So there is still some technological gap for the next years to still basically close here. And then, of course, when you look what you can do with silicon carbide in addition, beyond silicon carbide power devices, we're basically coming down here in this graph to have a quick look about integrated circuits. High voltage, of course, instead of discretes in integration. Urmimala just showed that for the gallium nitride ICs already. Of course, there's something similar in silicon carbide, which derives to silicon. But of course, overall, the idea in silicon carbide is to go to applications beyond silicon. Because let's be honest, silicon carbide is not a disruptive technology for silicon. The integration densities are much lower. We need some sort of high temperature metallization. So aluminum and copper usually will not work. So we probably cannot play the leading edge switching speed game here. So we're basically talking about applications where integrated circuits would be a nice idea, but silicon cannot perform because, for instance, of the high temperature or for integration aspects, and then even for pressure or other strain reduced efforts, where especially sensing applications where you're competing with standard mechanical sensor approaches nowadays at such temperatures might be very appealing. And this basically also stems from the properties of silicon carbide. Probably just quickly go over this slide. You should take the recording to have a closer look at these slides here. But I think the key message that I want to get along today to you is that we actually working on this silicon carbide CMOS technology by adding a PMOS transistor, what is then a typical CMOS circuit with all the aspects that you are well aware of silicon. And this actually makes it very interesting in silicon carbide that due to the lack of diffusion, if we manage to make some suitable retrograde profiles by ion implantation, which we can, it is actually not very much effort to put in place a triple well CMOS technology with just 3 implantations. So strain implantations, of course, in addition, then we have the implantation anneal, and then subsequently the process basically goes along with active area polysilicon, ohmic contact formation, and the high temperature metallization, which at the moment is platinum based. So from a processing technology point of view, it's pretty close to a silicon CMOS technology, but of course with some special additions, especially silicidation in ohmic contacts, implanting different elements, and then of course also using a different metal here. But it basically allows you straightforward integration of circuitry that you already know from silicon, which will suddenly operate at temperatures of 300 degrees C and above, like this SRAM circuit here, for example, or subsequent circuits that I will show you in a moment. And this, of course, always goes along with the possibility for more complex circuits to actually have good model prediction. And for that, we basically have SPICE models and also Verilog R models, which we can use in a PDK, so that more complex circuits can also be designed in advance. And that is basically also related to physical properties in the model, which is basically interface state density in silicon carbide, which you cannot so easily neglect like in silicon, and which has a significant effect on the subthreshold properties and the capacitance and everything. So it's quite helpful to actually have these kind of models in place so that you can also predict what technology development in an early access technology actually means to the models, rather than first having to try it out all the way. And of course, you can also use analog circuits like operational amplifiers, for instance. This is, of course, quite helpful if you want to do sensing and sensing applications, especially at higher temperatures, getting signal readings in the nanoamp range from 600 degrees C to a silicon circuit at 100 degrees C or maybe even 50 degrees C can be quite challenging, and some preamplification on the silicon carbide chip is very helpful. And here we basically, for instance, have demonstrated open loop gains in the range of 60 to 70 dB over a wide temperature range. And interestingly, or not surprisingly, silicon carbide actually performs better at elevated temperatures due to incomplete ionization at room temperature. So again, this is not a competition to silicon. This is something where you want to operate beyond the capabilities of the silicon circuits. And this also includes integration, like in a power module where you have a silicon carbide IC. You can actually stack integrated circuits on top of that with flip chip assembly. So there has been work to basically manufacture integrated gate drivers in silicon carbide that were then investigated and characterized as well. So this also, of course, leans towards the combination for silicon carbide power modules with very low inductive packaging as well, where you also want to exploit the high temperature capability of your power switches. So basically, if this device can go to 175 degrees, so probably will your gate driver. So it also should have a the high temperature rating that is required here. And technically, silicon carbide power devices could even operate well above 175 degrees. But of course, due to the assembly technology that are available and the gate driving circuitry, this is usually not fully exploited at this point. And we typically stick to the same temperatures that silicon power devices are using at this point. Yeah. Then, of course, there is a PDK similar to Urmimala's proposal or idea about the offer for the Europractice IC. We are also active in this field now, and there is also technology available through Europractice. So I think what Urmimala also mentioned about the Ascent Plus program, of course, also applies for our silicon carbide technology. And of course, our idea is to basically provide accessibility to the CMOS technology, similar to what the designers already know from silicon, so that basically the transition from the silicon to the silicon carbide into CMOS technology is not a big barrier, because you can use the same circuitry. Of course, you have to modify the chip areas, P and N areas, and maybe temperature compensation will work a little bit differently here. But overall, multi-project wafer and all these concepts, of course, will work the same. And then ultimately, of course, and this is also something that we're developing at ISB at the moment, is high temperature transistors, LDMOS transistors for an integrated half bridge, for instance. But admittedly, the challenge in silicon carbide is coping with the high electric field that this material can sustain. And here we are really talking about megavolt per centimeter. So for lateral transistors, other than a reserve LDMOS, it will be very difficult to sustain the high electric fields that are originating from the silicon carbide into the silicon dioxide, especially into the gate oxide here, even with speed plate designs. So that is why we're also following this reserve reduced surface field approach to actually also limit the electric field at the surface. And finally, going beyond this, we also noticed a significant attention from colleagues that are working in quantum electronics, because besides diamond, silicon carbide also offers color centers, which are suitable for quantum sensing and also qubit operations, which basically allow integration of these kind of approaches, even up to room temperature, in a technology where you also have circuitry available. And I don't think anyone has yet claimed diamond circuitry available. So usually you have a color center in diamond, the NV center, and then you try with a 19-inch rack equipment to basically make something out of the color center, because there is no integration of electric field or magnetic field manipulation around the color center, which we quite readily can do with pin diodes or MOSFETs that are basically integrated close to this color center. So here the idea for the CMOS technology is also to provide some sort of template where you basically can fabricate all the structures and afterwards basically create your color center inside this quantum structure to basically attenuate it with less additional effort. You probably still need a laser or microwave attenuation, but all the magnetic electric field stuff that can be more easily integrated here. So just to summarize, we are still seeing a lot of effort in silicon carbide technology development, especially towards the differentiation between different competitors in this field, towards having high integrated silicon carbide devices, which will be required to first fuel the needs of the automotive industry, but then of course also with that hurdle taken, and you can be sure that cost down is a key topic for automotive manufacturers. Other markets and branches will also be very much benefiting from this technology, as it is still quite young. And then, of course, exploiting silicon carbide power technologies to make integrated circuits might have a significant impact in sensing, signal conditioning, maybe even gate driver IC fabrication and integration, and possibly into quantum sensing. So we do see a quite matching application pool and technology push in this field, which of course is always the key requisite for innovation. And to that extent, I would also like to thank you for your attention, and we'll be happy to answer your questions subsequently. Thank you.
Thank you very much, Urmimala and Tobias, for your talk on gallium nitride and silicon carbide. It was very inspiring and a great introduction and overview of those two areas. I'd like to invite any questions now from the audience. If you'd like to unmute your microphone and pose questions to either of the presenters. It sounds like you did a great job there, and nobody has questions at the moment. Oh, Peter Ward has.
That's a super talk. Thank you very much. Talking about CMOS, one of the big differences between silicon carbide and silicon is the difference in P and N channel mobilities. Would you like to comment on that?
Yeah, of course. Nice to see you again, Peter. I think it's been a while, but yeah, clearly in silicon technology very much benefits from having quite matching mobilities. I mean, usually something like a ratio of 3:1 between NMOS and PMOS mobilities is observed. And with the main issue of NMOS transistors or N-channel mobility in silicon carbide being quite low, we actually see the same ratio, about 3.5:1, between NMOS mobility and PMOS mobility, because the PMOS mobility is not much affected by interface state density on the conduction band, on the valence band side. But since hole mobility is much lower than electron mobility, it actually has a rather low overall mobility. But since the NMOS is not that great, let's frankly put it that way, we still get something like a 3:1 ratio between N and PMOS transistors. And again, this is to say that we are not talking about leading edge, next generation high integration density for CMOS technologies. We're more talking about something like a 4004 CPU from 1980, which was like a 10 micron technology. I mean, nowadays, not something we would pretty much get excited for. But back in the days, it was a key enabling technology for integrated for PCs and computers. So yeah, that's the key idea here in fact.
So do you think that CMOS would work better in 3C compared to 4H?
That's an interesting question. I would say 4H silicon carbide at this point, of course, is the more realistic choice, because we have already the technology and the experience from that. But technically, since you don't need the highest electric field capability, and the channel mobility might be more of an issue, it might also be very interesting to consider 3C CMOS technologies. Indeed, yes.
Maybe this is something we could discuss at a later date.
Yeah, I mean, in silicon carbide, we're also not going to 800 degrees C, which probably would be the p-n junction leakage limit, similar to about 170, 200 degrees C in silicon. But then, of course, we would talk about gate oxide reliability at 800 degrees C. So we don't need that ultra-wide band gap to take a step beyond silicon. And C3 silicon carbide surely would offer that as well, in my opinion.
Thank you.
Thank you.
I see Jörg has a question there as well.
Yes, thank you. Hello, everyone. Thanks, Tobias, for the presentation. I think I have too many questions, but I have a really practical and technical one. Is there maybe you mentioned it and I missed it, but is there a PDK available to try this SiC technology you were talking about? I'm particularly interested in the sensor applications. It was interesting to see that you are talking about implementing an OTA or these kind of things. I'm working in sensor interfaces, so it'd be interesting maybe to evaluate how our topologies and architectures work.
So thanks for the excellent question. Maybe I was going a little bit too fast across this slide. Yes, we do have a PDK. We actually started with something that is more related from power electronics and just basically just usually do the layout and then have some design rules. But at this point, we do have a cadence PDK, which also includes the Verilog A models, so that basically for NMOS, PMOS transistors, you can put together your circuitry. We're also offering this through the Europractice website for download, so you can basically go through this down this road and get the PDK and have a look whether your circuits will be matching. And then we would also offer sort of open source is the wrong word, but we also would be very happy to integrate additional components like pin diodes or something that is particular for your circuitry that might not yet be supported, to also help grow and increase basically this PDK over the next few months.
That's great. And do we need to sign an NDA?
Yes, that is the standard way that the Europractice approach usually works, and we just basically followed like what you would do if you go to XFAB or AM Austria Microsystem, things like these, just basically for the convenience for Europractice, because the technology that we use is not like that kind of confidential like a company would treat it at this point, but then of course it helps us to maybe migrate to that point if some sort of PDK with an IP library or something becomes available in the future. So yes, we do have a standard NDA there for download that you would have to look into.
Okay, I see. Okay, thanks a lot, Tobias.